provides you more than one way. You can just specify that topology and then write command without worrying that it's going to blindly flood everywhere. Just like Dan said, if you set up a VLAN across the country, that's the first thing you know. It floods everywhere and then it just screw up everything. But with SDN, it's trying to change that. So Ryan is going to talk about the basic concept there, and then today walk through the software pieces so you have an idea. It's really, all of you are much more experienced in software engineers than I am. And so I hope that you can ask the right, whatever question you feel is right for you to understand the whole architecture, how things work together. To me, it's just a Java program running somewhere that is controlling a network, and then you have other software that can interact with that Java program, right? So it can be a Python program, you're orchestrating some other features, for example, identity, and then that software has some needs that you want to get information about the network or control the network, then you can talk to the controller software. So I'll leave that at this, and then just to let you know that now we have this Center of Next Generation Computing established. It's really getting CCIT as a whole team. We're getting all the expertise that we have within CCIT to work on these forward-looking projects. And it is not just research. GENI started off as a research project that NSF wanted to build this research environment so that researchers can do stuff, but they forced that infrastructure to build on production environment. And that actually is crucial. So eventually this becomes a production infrastructure. Many of the software pieces, best practices people come up actually can work with production systems. So we're actively discussing what are the software projects happening here, how can we leverage that interaction and then try to put in some of these advanced pieces into it. So I'm sure that many of you will get a chance pretty soon to engage in these kind of So Ryan, I'll hand this back to you.
Okay. Well, Dan and Dr. Wong gave a pretty good overview of the first few things I'm going to talk about, but what I'd like to do is go in this order here. I'd like just to give you, for those of you who aren't familiar with it, to talk about SDN in general and OpenFlow and how the two are related. And then I'll give some potential use cases from the software developer's point of view, or maybe a third-party app. And then we're actually doing a lot of research ourselves with SDN and OpenFlow in our lab, and so I've highlighted some of the projects we're working on, so give you some insight into maybe what you can actually do with SDN. And then after that, we'll go into a little bit about from the switch, the hardware level, all the way to the controller, and on the hardware level, and also any applications that want to communicate with the controller. I'll talk about the software and the hardware on all those, so you can get a good idea of how they're all interacting with each other. And then finally, I've got a VNC connection up to an actively running hardware controller in the lab. And so I can pull that up, and you can see it will just be debug output, but I'll restart it for you, and you'll be able to, after I talk about how to write a full byte module and how full byte actually works, you'll be able to see the types of processes I've been talking about prior to that actually happening in real time. And feel free to interrupt me if you have any questions, and I do tend to speak softly at times, so if you ever kick me, just tell me.
Speak up.
Okay, so first off, what is software-defined networking and OpenFlow? SDN is the physical separation of the control plane from the data or forwarding plane. So in traditional networks, you have a switch with the data plane and the forwarding plane and the control plane all on the same device. With software-defined networking, is this concept that you leave the control plane and the data plane on the switch, but then you make a centralized, so you leave the data plane and the forwarding plane on the switch, but then you make a centralized control plane, and that's also known as the controller. The controller is centrally managed and it's directly programmable, and because you're using a single entity, namely the controller, as the control plane, you're kind of abstracting the entire hardware infrastructure of your network from the user. And so here's a graphical depiction of software-defined networking. So on the bottom there, you can see there's some network switches. And on those switches, that's where the physical packet forwarding takes place. And the red lines going up to the network operating system, that signifies that's the control plane that's been taken away from the physical devices, and it's in one centralized location. And the control plane can extend it with whatever features you'd like to for your given application. Now, OpenFlow, on the other hand, is kind of an application of software-defined networking. OpenFlow, there's the concept of OpenFlow, then there's the OpenFlow protocol. The OpenFlow protocol is what links the physical devices in your infrastructure to the control plane, namely the OpenFlow controller. And using this OpenFlow protocol and OpenFlow concepts, the switches and other network devices can communicate with the controller, and you can actually do some really cool things. And so here's the same figure, but modified a little bit to reflect how OpenFlow comes into play. So notice on all of the control interfaces where the physical or the switches are linked to the control plane, those are OpenFlow connections. And instead of a network operating system, it's an OpenFlow controller now. And the OpenFlow controller can provide traditional network services. So for example, if you connect an OpenFlow controller to a bunch of OpenFlow enabled switches and don't change the controller at all, then your network will function just pretty much like a typical network. However, you can extend the OpenFlow controller, especially if it's open source, to do pretty much whatever you want to. And you can do that through custom services that you actually code up on the controller itself, which I'll show you at the very end. Or you can do it through APIs on the controller and maybe do it from a third-party application someplace else that will communicate with the controller over the network. Okay, so what I'd like to do is just show you a quick animation that describes how software-defined networking works, just for a basic example where one client wants to communicate to another on the network, and let's assume that the network has just been plugged in and turned on, so it does nothing right now. And this will be in contrast to a traditional network. So unlike a traditional network, a software-defined network has, or an OpenFlow software-defined network in particular, has an OpenFlow controller, which I show on the right-hand side. That controller connects up to the network using the control plane. Now, the control plane can reside on the same network that your data does. However, it is common to physically separate the control plane for security reasons, for one. But as long as the controller has a connection to each of the switches, then they are connected. And this is being done through OpenFlow. So let's say we have one user who wants to talk to another. The first user will generate a packet, and just like normal, that packet will make its way to one of your OpenFlow enabled switches. Now, if your switch has just been turned on, of course, it does not know where to forward this packet to. So in a traditional switch, what would happen is that packet, or the switch would determine, after some broadcast, would determine which port that the destination client resides on, and would insert an entry into its table. Now, for a software-defined network, the control plane is taken away from the physical devices, and it's been elevated up to the OpenFlow controller in this case. So when the switch first receives the packet, it doesn't know what to do. So it will generate an OpenFlow packet, which it sends to the controller. Now the controller will, based on what it knows, it will send a response back to the switch, and then the switch will insert what's called the flow. And that's basically a mapping from one port to another that will define any subsequent traffic from that particular user, just to follow that flow, so that the whole process of going up to the controller and requesting how to route the packet only happens one time at the very beginning. So then that packet will follow the flow, and let's say it gets to the other side of the network that's also connected up to an OpenFlow switch. Well, that switch will go through the same process. It doesn't know what to do, so it will query the controller. The controller will send a response, and another flow will be inserted, and the packet will make it to the user. And so any packets that come from here on out will simply just follow those green flows there, and they won't actually have to talk to the controller. Of course, the flows can be typically configured with a timeout, so after some time they'll disappear, just so as to not consume all the memory in the switch. So, does anybody have any questions so far? Yeah.
Earlier was using like a generic switch
So I'll get into that kind of at the end, but start talking about the software. But a traditional traditional switch can be used as an OpenFlow switch, assuming that the hardware on the switch, or assuming that someone's written a firmware that's compatible with the hardware on that switch. So
The majority of Ethernet switches exist today, they share a very similar architecture. They don't have a full table, they don't have a driver on board that is actually configuring those flows. So many vendors are opening up that interface to all flow protocols and try to do many different vendor switches. And then the trend right now is going forward, many of the white box switches are going to come out. So these are merchant cinema much cheaper switches, but then it come and then you have to control what the software is talking about.
You could imagine that there are large network vendors who spent decades developing their control planes and everything to be a certain way, and suddenly we introduce this protocol that makes it where I don't care about any of their control planes. In fact, I don't want their control planes. So the large vendor network switches typically do not implement OpenFlow, or don't implement it fully, or don't implement it as well as the other control planes. So we're kind of stuck in this strange land right now where the big network vendors are making like they believe in this kind of stuff, but not really releasing switches that do it. Meanwhile, the white box has generic switches that are sitting on golden opportunity with devices that have robust OpenFlow environment. So as a prototype that we just set up, and I just looked at these switches, and I took out all the 10-gig switches, one's a 40-gig switch. And I took out all the ones that you pay that are not common. There's 14 lines of configuration. Now in the production context, you want to add some more for network monitoring and stuff like that. But we can add additional networks, all kinds of things to the switches. But we can touch the configuration. That's 14 lines. I think it's 4 lines different. And you can go up to one of the key nodes and you can plug it into a different port. And the controller will realize that it's weak. And it will adjust the plug. So it's really neat. Now the other part of this is one of the diagrams. It's not just physical switches, it's also virtual switches that are on hypervisor. And the virtual switches basically make this configuration. So that becomes the common factor between the hardware and the software.
That's actually one very key point. Later on, Ryan's example really show most of the things you really care. You start from the edge. So the edge network, oftentimes you can actually install from Linux. It already comes with a virtual switch, open virtual switch. But then there are other kind of virtual switches you can install in your Linux environment, and then you can do your SDN type of management here, and without even worrying about the core of the network. Everything is software. The switches are software running on your host, so you have full control.
Would it have been possible also when this tech came in on the first one of those controllers put the flow on the second switch before it got there?
yes, so if the controller knew at the yeah, so it would. So if the controller knew at the time that's where the second user was, then it could do that. And so so that's what the circuit pusher application would do, something similar, similar to that, right?
Well, the circuit pusher, so you can do this directly within the controller. You write a code module saying that if you know the source and destination, figure out the path, and directly send out to configure all the switch that's involved. Another way to do that is they have a separate module called the static flow pusher that is you go out and then you want to directly specify explicitly what is the path, what are the switches, and then you set up the path yourself. So that's a sort of a module that takes a fully automated one out so that you have some visibility, and if you want to control yourself, you can do that.
Okay, so then we can ask the question, why do we care about software-defined networking and OpenFlow if it's pretty much doing, so far from what we've shown, the same thing as traditional networks and switches do? And the reason being is, and Dan highlighted a lot of these, is that traditional networks, you have to configure each switch typically one at a time, and there is no centralized location where you can control everything at once. In addition, a lot of traditional switches are closed source, and sometimes you have to have a lot of vendor-dependent devices. So if you want to have a big, I'm not an expert on this. I've never really worked with. I just kind of got thrown into SDN. Didn't do much with traditional networks before this, but what I've heard is this is like Cisco networks. If you want to have some cool feature within your network, you need to have all Cisco devices, and they all need to kind of speak the same language and work together that way. And so you may get stuck into buying things from one vendor, or you may be stuck in the product cycle of a vendor waiting for the next one to come out. And just for that, the last one is decentralized control, so everything kind of operates independently. And I guess that's kind of the same thing as what I said at the beginning. But
For instance, you have a great idea on a layer 3 protocol to replace the internet protocol, for instance, and you just want to try it out and scale. In order to make that work on a traditional network device today, you need to take that idea, get it through all the IETF committees, and get all this, and maybe in 10 years your protocol might actually get implemented on a network hardware. By then the problem that you were trying to solve would not probably be relevant anymore. And so if we wonder why we're using the exact same internet today that we are in 1981, this is the reason why. It's very ossified, is what we call it. So that's one thing.
Okay, so contrasting traditional networks to what SDN and OpenFlow can provide, with OpenFlow you have a very dynamic software architecture, mainly that the control plane is in one place and it's entirely programmable, so you can do whatever you want to. And typically a controller will come with everything necessary to do what a traditional network would do. So if you want to extend that, it's very easy to do that. You just add whatever you want to the controller, you can handle the packets however you choose. In addition, a lot of OpenFlow controllers are open source, so you can view all the source code and make any changes you want to. So say there's a traditional network type feature that you want to change, maybe test your new protocol, then you're more than welcome to do that. There's nothing to stop you. And also, SDN networks allow for large-scale network research, and the ones I've highlighted in red here I'll actually touch on in some examples that we're doing. But you could implement a new quality of service approach, apply some new mobility scheme, access control, data migration, security, and anything that you'd like. Any OpenFlow controller will support the integration of custom network services. Some of these you can have on the controller, and they can be completely transparent to the end application, or to the end user's application. And one of the examples I talked about is actually that. So the end user doesn't have to do anything at all, it just uses the network as if it is a traditional network, and all the OpenFlow SDN stuff happens behind the scenes. Another thing you could do is have some sort of API on your controller where the application that the user is using maybe asks the controller to do something special for it, maybe to transfer a large amount of data. So those are the types of things that you can do with the software-defined network, and that wouldn't be quite as easy to do with a traditional network. Okay, so just briefly, I'll touch on some. These aren't the examples of research that we're doing specifically, but these are some potential use cases for SDN. Maybe you have a large amount of data that you want to transfer, and you're operating on maybe a congested network. And you could, if it was an SDN network, you could send a message to the controller saying, "Hey, I want to transfer this much data. It's going to take me this long to do it. Can you give me a large bandwidth path for this amount of time?" And so the controller, through that method, could guarantee you that you have the bandwidth you need to transfer the data that you need to and the time that you need to do it. So that's one example where SDN can come into play, and that's also kind of a quality of service type of mechanism. Another thing is handovers. So an example that this kind of ties into another example I'll talk about for our research, but you can do actually implement a mobile IP approach and for vertical and horizontal handovers using software-defined networking. So with mobile IP, typically you use IPv6 if you want to have really good mobility support, but we've actually implemented a IPv4 support for mobility using software-defined networking. And also you can do multimedia stream management, for example. So, and this is also another kind of leads into another example I'll talk about, but using software-defined networking, you could set the paths you want for certain video streams to travel on, and rather than you broadcast it to however many users you want, to simply just report for each one. It would be as easy as that. another common thing would be security. So say you have some really secure traffic that you want to be completely isolated from anything else, you can put that on a special path that you know is a secure path from the source to the destination, just by asking the controller to do it for you. So now I'll talk about some of the projects that I've been involved with the last couple of years at Clemson. And the first one, some of you may have heard of it, and it's called Steroid OpenFlow Service, also known as SOS. This was a project that I passed to at Clemson, and I've been tasked with porting it to the Floodlight OpenFlow controller, which is what I'll demo it, or the controller I'll show you at the end. Steroid OpenFlow Service is designed to enhance large delay TCP connections over a large delay bandwidth product network. And the reason that this would be useful is because of TCP window sizes, for one. So say you wanted to transfer a large amount of data from one side of the country to another, and so you have quite a bit of delay in between both nodes, and so with a typical TCP window size, you're going to send some packets, but it's going to take you a long time for the packet to come back before you can send anything else. So using software-defined networking, we are going to buffer locally at the source end a large amount of the client's data, and then set up many parallel TCP connections across the country to the other side, where they would be activated back into the single TCP connection and sent to the client. So this is a service that's actually completely transparent to the end user. And here's a graph here or a picture that kind of depicts what I'm talking about. So look at down the right, actually you have your client. And the client will start off a TCP connection just like normal. It has no special software installed on it. And the OpenFlow switch that the client's connected to will detect this TCP connection. And the OpenFlow controller, which is common to both sides of the network, will redirect the client's packets to a local SOS agent. This agent will store a buffer of all the client's data, and it will act the client as if it were actually the original intended destination. So the client thinks it's actually making it all the way across to the other side, but it's actually something that's delivered to its local network. So this source SOS agent, it's called, will set up potentially hundreds of parallel TCP connections to a destination SOS agent on the destination side of the network. And so the same process will happen in reverse, where all those parallel TCP connections will be aggregated back into the single one, and it will be presented to the TCP for the destination strings the server down as quickly. And the server will act, and it will go to the SOS agent on that one instead. So that, as you can see, that the whole process is masked from the source and the destination, and it's just completely transparent. And that's a very practical place for software.
Yeah. So say the client's crossing the server in California. Where is the OpenFlow controller?
The OpenFlow controller could be Clemson, and as long as you had maybe it was a public IP, or as long as it's addressable from. So as long as the OpenFlow switch on each side can see the controller, then you can control it.
So in today's GENI environment, they set up an engine there to sort of like for you across, say, Clemson and California. And then they carve out a slice on each switch. So basically, it's logically associate each switch with your controller wherever it is. So if I run a Clemson controller, then now temporarily I will be given the permission to control the switch in California and the switch in Clemson for this particular connection purpose. But in the future, they are discussing about it's possible that Clemson will run Clemson's controller, and then California and Stanford probably will run their own controller. But then because they can communicate that they will be setting up each side's network using their own authority, but then achieve the same application. That makes sense.
So they would get their first permission to our controller to
Right. So they will probably tell us, hey, I need this path with this attribute. Did your controller install the right entries into the switch so that you will recognize them?
It's a little longer the personal relationship with trust.
Yeah, have to be organization trust so that you allow them. So right now within GENI, all the university participating already signed an agreement saying we agree any GENI user come in is an separate So you can just treat it, GENI as a nationwide national test bed for future internet research. So basically, university, I don't know how many now, but they install some of the network equipment and some of the computer servers, and then offer them as GENI research. So when you go through one single GENI portal, it's a software service. You can reserve an end-to-end path across the nation. It will basically send out all these reservation requests to each campus, and each campus will accept those and set up the access method.
It's a nationwide at scale test bed What's broken?
Brocade is not considered a piece of resource, it's actually a campus resource that you build up. So it's a campus level gateway. GENI can be a subset of traffic that eventually leverages that gateway.
It's an active global environment
But the reason as the name comes out, this environment, it emphasizes it's just not just about network, not just about computer servers, because in the past there are already test beds that look at each individual. And now this test bed is provided with one whole environment, you can control everything. The software, the storage, and that.
So, since you said the client doesn't do anything special, is it
The SOS, yes, it does. So when say a TCP flow say a client just starts up a new TCP connection. Say your client starts up a new TCP connection, there won't be flows for it in the OpenFlow switches already. So those packets will be sent to the controller, and the controller will know this is a new TCP connection because it's receiving packets. So then it'll insert the flows, and any TCP packets after that belonging to that same TCP session will follow those flows. And so if another client decides to set up a TCP connection, that same process will happen again for that one.
One thing important for this as a research prototype, basically any TCP flow initiated will be handled this way. But if we want to make a production, then we need some mechanism on distinguishing which are the flows that we want to serve it this way, and that probably linked to some identity solution on the campus side that we can.
the identity solution has anything that
Do it in box.
Okay. So that is the first project that we're working on now. The second one, and this is the code I'll show you at the end in Floodlight. This is a mobility project over heterogeneous wireless networks. And what that means is performing a handoff between either maybe Wi-Fi to Wi-Fi, which is common, or more exciting, Wi-Fi to WiMAX. And so at Clemson, we have 3 WiMAX space stations. One of them is on campus, mounted on top of one of the high-rise dormitories, and the other 2 are in Greenville. And we also have some GENI Wi-Fi access points. So we have a WiMAX and Wi-Fi test bed, and they're all both overlapping. So that provides us an opportunity to implement, or try and implement a vertical handoff solution. And that's just what we've done now using software-defined networking. And it consists of 2 main components. The first one is the network level. On the network, we detect that a client has migrated, and then we also insert flows in the network to route packets to the client wherever it may be. So if the client's first on Wi-Fi, when it connects, we'll detect it's there because it just connected. We'll insert flows along the path from the root of the network to the client, and so any packets destined for the client will follow those flows. And any packets leaving from the client will follow the flows out. If the client moves maybe to WiMAX, those flows will be removed, and new flows will be inserted depending on where the client is. Now, the other problem is, if the client moves to a new network, in order for it to be mobile from the application's point of view on the client, we need to maintain the same IP address. So we also manage the IP addresses within the Floodlight OpenFlow controller. So I have a DHCP server, I'll show you at the end, that manages all IP addresses for the clients on all connected networks. Now, for the client level, whenever a client switches interfaces, if it's maybe a break before make connection, the socket will go down because the interface goes down. And so to prevent that, we actually create a virtual interface using an OpenV switch, which is a virtual OpenFlow switch. And the client, all the applications in the client will communicate through that one virtual switch. And so we mask which physical interface the client's actually using from the applications. And so using a separate floodlight controller running on board the client, we will switch back and forth between the physical interfaces from that virtual interface. And by doing that, it will be transparent to the application. So on the network level, this is kind of a mobile IP approach, where instead of the home and foreign agents, if you're familiar with mobile IP, we have the OpenFlow controller and OpenV switches. And instead of tunnels between the home network and the foreign network, we're simply using OpenFlow flows. And the DHCP server is on the floodlight controller. For the client level, what actually initiates the vertical handoff is the change in interface, but like I said, the socket would break, so we use OpenV switch and the floodlight controller to mask the bringing up and down of the physical interfaces by a virtual interface. And so by doing so, we manage all the physical interfaces using software-defined networking. We'll insert OpenFlow flows between the virtual interface and the physical interface we want. And so the end user's application always sees an interface that's up. And so combining that with the network side, if we issue the same IP, the application socket never breaks. And so this is kind of what it looks like on the client level. And my figure's going off the screen for some reason. But each of the orange boxes there, those represent a physical interface on the client. And each green box represents a virtual OpenFlow switch. So notice there's one virtual OpenFlow switch per physical interface. And that's how we are able to insert flows on a physical interface, because we have to have an OpenFlow enabled device. So by installing a virtual OpenFlow switch, also known as an OpenV switch bridge, we can bridge the physical interface to an OpenFlow enabled one, so that we can insert flows between this virtual OpenV switch bridge. They're all virtual, but this OpenV switch bridge here, this is what the applications will communicate through, and then we'll insert flows depending on which physical interface we want to use. And we've got floodlight. This is what controls insertion and deletion of flows. So, have any questions about this?
You actually say the application is communicating with floodlight rather than the
Yeah, but the application sends traffic through
the traffic.
So another component that's missing from this diagram here is what actually controls the switching of interfaces. So using floodlight REST API, we can add and remove flows from the application. So we could foresee that we don't have this set up right now. We set up a script that says switch to this interface, this one, and this one. But the application could actually control that using floodlight REST API.
What happens if the client snaps into the Wi-Fi or not?
So the other time you're virtual now, and that's also true of these ones here. They're directly connected to the physical interfaces, but this virtual interface will remain up even if the physical interface is. Right. So Fallback has what's called a forwarding module. So basically, I think that's the one switch module. So they have a controller that doesn't really do it, it's automatically. I'm not sure if it's illustration. But this fallback has the forwarding module disabled, meaning that if this isn't accurate, it will delete this block unless we manually what's in the forward. So this has a flow pressure we dictate exactly.
Getting higher. And the advantage is having that switch where you walk into this building.
Single standoff.
Yes, single standoff is plus.
collaboration as
So the network level and the client level, they work collaboratively. So in the way we do that is it's all client initiated, so the client will issue a DHCP request, will accept it, and then the side which is actually great. This is, I debated on putting a different picture up here, but it's way too detailed, so I just opted for this animation instead. So this is what happens on the network side. So there's somebody in a mobile situation, and he generates an initial packet to, or tries to connect to this WiMAX network. So this packet will go up, and these green flows there, those are flows that we pre-inserted on the network side to intercept all DHCP packets. And all these, the way we actually have it on campus is we have routers running Linux, and we've installed OpenFlow, which is the OpenFlow virtual switch, on all of these routers, and also on the WiMAX base stations, the gateway behind it, we've also installed a vSwitch. So just using Linux boxes, we can intercept all these DHCP packets using those green flows there. So the flow will capture the DHCP packet, send it to the controller, because the flow is going to define anything coming in on the switch there, send it up to the controller, which is a special port on the OpenFlow switch. The controller, because it's running a DHCP server module, will know what to do with that packet. And then it will reply. Once it replies, the client will be able to use the network, then the client will roam, and it will try and connect to a different access point. So the same thing will happen again. Oops. The packet will get sent from the switch up to the controller. It's the DHCP packet. The controller will reply, and the client will get its IP address. And because we're running our custom DHCP module, the client will get the same IP address because we're ensuring that. And the way we're actually doing it is by maintaining a list of all the MAC addresses of every interface on the client. So we can see the request from the valid MAC address, we know what IP to give. So it's kind of an extension of a traditional DHCP server in that more than one MAC address can work with a single IP. In those yellow flows there, these are what gets inserted after the client migrates. So actually what we're doing now, this is a change that happens not too long ago, but we have another OpenFlow switch at the root to avoid this triangle routing, which we'll see in a second. But remember, the client was initially on the WiMAX network on the right. So that's its home network. When it migrated, it went to this one on the left, which is the foreign one. The yellow flows will bounce all the packets that are being routed by traditional networks to its home network. We'll know, therefore, our client once they get there. So we'll bounce them all back to where we know the client is right now using OpenFlow flows. So any packet coming out from the client will simply go out the network. It doesn't have to follow the triangle back to the side. But what we've done recently is we have another OpenFlow switch at the root to completely avoid that triangle back. So any questions about that network level? And so this kind of works collaboratively with the client level I showed you just before. So the client level sends the DHCP request, and we rely on that DHCP request from the client in order to detect it on one network or another. So a part of that is we have a script that will force that DHCP request to happen every time we try and change interfaces.
So how macro
So what we're doing right now is we're assuming knowledge of all the MAC addresses of the client and the DHCP server. But what I'm working on right now, and hopefully in a few weeks will be done, is just adding a DHCP has a lot of option codes. Some of them aren't used. So making a custom option code in a DHCP packet and injecting a list of MAC addresses in the initial connection to the network, so that when the client first connects, we'll learn all the MAC addresses that it's going to be using. Did I answer your question? Or, it gets down to layer 2. So you can, for example, you can match packets based on the layer 2 address, or layer 3 or 4. Right. We're talking.
So that's why.
And that's what I see the do. Right? So the user actually has the control on forming the control layer. What is the association I want? So if I have 2, 3 interfaces, I go through some authentication way, tell the controller these are all valid addresses for the MAC address. And using the MAC address in order to provide the So to me, it's a really pluggable architecture. You don't really care if you swap out some devices. Tomorrow you get another new card. If you register with the server again saying I have this new MAC address, then again, it immediately works.
Keep in mind, these are just examples. Like, you could implement whatever you want to. That's really the point. Like, the problem with networking today, as I see it, is the way we solve problems over the years. Every time we run into a problem, we push through standards body and develop a protocol. So we now have this stack of protocols, thousands of laws, and there are no layers of abstraction in the network at all. So a really good talk to listen to is one by Scott Schenker, and it's called the Past Protocols and the Future of Networks. And that's one of the things that he talks about is how you can use software-defined networking, how software-defined networking should be used to have layers of abstraction. Just like in programming today, you don't necessarily always think about what the registers are being turned on and off. You can just let it go. In networking, let's go through the network. So it's very hard to make a network do something which ought to kind of just work, but what I'm demonstrating is that it's a challenging process. It doesn't really work that way. Unless we've been
Okay. So the last.
Well, the priority here is different. So here it's about the package priority in terms of the language mediation, right? So like OpenFlow content, when you say priority of 4 entries, that's saying that if you have one traffic matching 2 different rules, you will match the highest priority rule. So that's a logical given. Once you install those rules, it's fixed. But here we're talking about if you have multiple kinds of traffic, then you have the ability to put it into different boundaries allocations, right?
Yeah, or if you have like a 3G and a Wi-Fi connection, you can put it on switch. So that's more
I really thought there was probably lower levels of different types of things like wired versus wireless. If I have wireless, I'll so that level of development is one level above the flow entry. So you will probably have a process here that actually differs. You know the three interfaces with the crossflow, let me choose this one, and then you call the standard flow equation. You install them whenever you have that available.
So this project here is actually designed to be an SDN for people who want to evaluate such things in a cost or in a particular way. So they can, using this framework, expand upon it to do something. This is a part of it. This is a GENI project, but we're tasked with designing a vertical handover test bed. So you could develop such schemes using this framework. Okay, so the last project I'll talk about today is what is called GENI Cinema. This is a new one that we've been working on it for a few weeks now. But what it is it's a software-defined networking OpenFlow video streaming service. So what happened, and this is a work in progress, we're just really just getting started with it in the last couple of weeks, but what happens is a client will connect to a public server, which will have a known IP, and kind of like YouTube, you go to YouTube and you select the video that's of interest to you. So when you select that, the public server will tell the client, it will redirect it to its closest GENI Cinema gateway, which could be at a GENI enabled or a GENI participating university, such as Clemson. And so all of the client's packets will go to that gateway. Now, on the other side of that gateway, using OpenFlow, we will insert flows throughout the OpenFlow enabled network to route those packets to the video server and to the video that the client's actually interested in. So what that looks like is this here. So say we have clients on the left side here. Those are all the laptops, and they're all connecting up to the internet. And they go to a public server, and there that's where they select the video. And that server will redirect them to the nearby GENI Cinema gateway. On the other side of that is the GENI network, consisting of OpenFlow switches. And then the fallback controller, which is the large thing over on the top right, that will insert flows depicted by the dotted lines there in between all the OpenFlow switches in order to get to the server the client actually needs to go to. Is there anything else I should say about that? That's all.
This works both ways. It's both uplink and downlink. So we were funded on this project because we proposed to make it a production service that is for any university. It could be a GENI capable university or a regular university network. So based on your IP address, you will discover what is the closest gateway to connect you to that network, to the GENI network. So the idea is, before we wanted to go in GENI because GENI we have full control so that we can always deliver the multimedia stream on the best path. But once it gets to the closest gateway to your location, then it will use whatever existing. If you have IP network, fine, it will use IP40 representative. If you're on a GENI network all the way throughout your campus, then we will just use the OpenFlow. And then we want classrooms on campuses. If I'm, for example, today we're giving this talk here, I could have set up a camera and directly take that video feed, send it into the GENI network, so that anyone else on other campuses know about this event. They wanted to take a look and join in the seminar and watch the video. That's the whole idea. We're just trying to get this, and that's what we're building it up right now.
From the camera, obviously there'll be a single point or server. But in this case, you're showing multiple servers. Is this a synchronized system, or is this for a service as you build that?
So what we see is it's like a load balancing architecture. So from the client, whenever they offer, say, I wanted to upload my video stream, going through that public portal, it will be informed of a particular IP address. That IP address could be actually just a virtual IP address that maps to many possible servers, and then within GENI that will retrieve the server and will handle that much more.
These should be synchronized with the others, or is that a
It's just a single server right now.
self-service?
Okay, so the next thing I'd like to talk about is probably what a lot of you are interested in, and that's what are all the software components from the switch all the way to the controller and all the way to any application you may write that uses an API on the controller. And this is be specific to an OpenFlow software-defined network. So recall this is what a basic software-defined network looks like here, where the control plane is simply elevated up from the data and forwarding planes, and the control plane will have certain features. Now, OpenFlow software-defined network extends that by using the OpenFlow protocol in between all the OpenFlow-enabled devices. They connect to the OpenFlow controller, and the controller has typical network services, like basic forwarding that you find on a traditional network. It also has custom services, which you can write code that just lives on the controller. And then there's the external APIs, like the REST API, that external applications can use to convey information to the controller and maybe make special requests. Now, from the switch's perspective, this is the hardware. The switch must be an OpenFlow-enabled switch, meaning it must support OpenFlow in some way, shape, or form. And typically, that's just with the OpenFlow image on it. Like the Pika 8 switch, for example, uses an OpenVSwitch firmware. So the OpenVSwitch virtual switch that you can install on any Linux platform, they've ported that, and they actually have it running on board the switch. So if you're familiar with With a vSwitch, you can easily use OpenFlow firmware. So you just power it on, it goes to the bootloader, you select the OpenFlow firmware, and once you boot up, you get what you see on the right there, where you have your data path and the switching hardware, you have your flow table, and the flow table is where the controller will insert entries telling packets how to be forwarded once it initially learns where to forward the packets to. And on top of that, you have your control path, and followed by that OpenFlow component, and that's actually what's going to link the hardware, the software of the switch to the controller. So now, extending this a little bit, we have our switch on the bottom there, which is what I just showed, and now we have that OpenFlow connection seen in there to the controller. And on the controller, you have whatever hardware your controller is running on, or whatever operating system it's running on. It could be Linux, Mac, Windows, whatever you want. And then you have your OpenFlow controller just simply running as an application on top of that. And in the case of Floodlight, which is the OpenFlow controller we use, it's in Java, so you can run it pretty much anywhere. So on top of the OpenFlow controller, you have what I showed earlier, the basic network services, any custom services you add directly on the controller, and also the APIs the controller provides. And you can also add more APIs if you want to, since it's Floodlight in particular is open source. So notice, well, you can't actually see it over on the right here. For some reason, it's cut off. That same red OpenFlow path that's actually good links from the OpenFlow from the switch all the way up to the controller. So, okay, so the way that the switch connects to the controller is the one thing you have to do on the switch is you got to tell it where to look for its controller at. And so you do that by specifying the IP and port number of the controller. By default, the OpenFlow port number is 6633, which I show right there. And you can set your switch into what's called standalone or secure mode. Standalone mode means that if the controller all of a sudden disconnects from the switch, meaning that that's bad because the control plane is now disconnected, the switch will default to a standard network switch state, and so your network will still run if that's the behavior you desire. However, a secure mode means that all traffic will halt unless it actually sees the controller. Now, that doesn't address problems with the security from the switch to the controller, which you can either do through TCP or TLS. But if you use TLS, that's a little more secure.
Think of it like on the telephone network, you have CMON system, which is what tells the telephone switch is what like this is the exact same. Only as well as the applications all see control of the rest of the ground. There is a line that's and it is a big concern. So there's nothing to stop me from contacting the controller and the care that application. Obviously, they're the same name as the
So that's not a technical limitation, but a limitation.
it's not there.
This particular version is an open source software meant for academic use, so they didn't put any restriction. The commercial ones normally will have authentication, even if it's an ingress request. Session cookies installed.
So make your big bucks by connecting the controller
And if we have the expertise here to quickly add up some authentication in this software, I suppose that would be
Understanding. People always develop something and say we're doing this. Makes it harder. It's easier. Why is it better? That's okay. So it's
All right, so after the switch makes its initial connection, then the controller will try and learn what's actually connected to the switch. And it'll do that by sending out LDP packets, or link layer discovery packets, out into the ports of the switch. Now, if you have multiple OpenFlow switches in your network, the controller can learn how all the OpenFlow switches are interconnected by sending an LDP packet out on a particular switch and then listening for it on any other OpenFlow switches. So the controller can learn the whole network topology by doing that. And they can also learn, well, what devices are physically plugged up. Okay, now this extent, so this is how, and again, the right side is cut off for whatever reason, but over here I have in the API of the OpenFlow controller, I have a green arc similar to the one over there, connecting over to the, so that up here is the application, which could be a third-party application, controller, and using the complex REST API, for example, that application can communicate to the controller through its REST API, and then the controller will then relay any message the application sends to the switch. With the REST API, you can do a lot of different things, and I'll show you that later on. You can simply query for things, and you can also actually make changes to the network through the REST API. Okay, now how the application connects, how a third-party application connects to a controller through an API is, of course, controller dependent. Floodlight has the REST API. I can't speak for any other controllers because I've only ever used Floodlight. But Floodlight's REST API works with JSON, so any data it spits out can be easily readable. There's a lot of JSON serializers and parsers, so it's easily compatible with any third-party application. And like I said, you can modify the physical configuration of the switches in your network through the REST API. You can also just query for information. Okay, so now, unless anybody has any questions, what I'd like to do is just talk specifically about the Floodlight controller and then just give you a peek at some of the code that we have and show you how to start off writing code in Floodlight and work your way up to a module. And I've got a VNC connection to the actively running the mobility vertical handover code. You can actually see I've got someone testing out a WiMAX adapter, so you can see him making requests and seeing the flows being inserted and stuff like that. Yes? I don't believe there's anything built in for that. Right, so
So that will be as an issue. There will be a module within Floodlight that you're going to have delivery logic that's used to detect that. So for example, when you first learn about the MAC address, you keep a record of the location, and then based on some criteria, you consider some activity. Yes, because the controller naturally have the visibility of all the new MAC address showing up, and you can check the history.
So for example, if you currently have a MAC address pointed to one port in the controller, you will see this new MAC address, which is the same MAC address pointed to another port. It can probe to see if the other one's still connected to your port, and in that case, you can tell it's something needs to
Possibly write a module to work against a authorized list or database. New MAC addresses are authorized. That's the good thing about the controller speaking is writing software.
Doing that, you don't even need to touch the controller code actually, because you already have a REST query. You can get all the current connected endpoints and the hosts, and then with the attachment points. So now, if you periodically query that and then you put your Python code, you're querying this Floodlight controller with that information, then you can achieve that without even adding a Java module to the controller itself.
I guess the way that people started on that is one of Floodlight's basic tutorials online is how to just walk you through how to run a module that just listens and logs MAC addresses. So that'd be a really great way to start with implementing such a thing to detect MAC addresses. Yeah. So, any other questions? Okay, so the floodlight controller is open source, which makes it great to work with. You can see everything from the ground up, and you can change things that come with it off the shelf if you don't like it. But more interestingly, you can add a whole bunch of stuff that can be really cool things, like the research examples I've showed already. Floodlight's written in Java. It's sponsored by Big Switch Networks. It has a very large support group and a developers or support developers group. If you ever have a question or having trouble, you can send an email out to the group and you'll get a response back within minutes, no matter what time of day. It's typically the same person every time. I don't think he ever sleeps. But there's a lot of support in the Floodlight developers group, and so I highly recommend that as a controller to start off with SDN. And like I said, it's easily modifiable, and the way you do that is by either modify existing portions of the code, or you can write your own modules, and you can think of them as pretty much plug and play with the existing code. And you'll see how that works in a second. And you saw the Eclipse image there. You can Floodlight, you can import it directly into Eclipse, which if any of you have used Eclipse before, is a really nice IDE, and it makes it really easy to modify code on the fly, just recompile it and run it. And it makes it really easy to write the code. So what is a Floodlight module? A Floodlight module is basically just a Java package, and you can write a module to do whatever you want to. So you can have it time triggered, or you can more commonly have it triggered based on some OpenFlow event. For example, every time a switch receives a packet and the switch doesn't know what to do with that packet, they'll send it to the controller, and that's what's called a packet message. And then you can have access to that entire packet, including what port it came on, what switch it came in on. And you could do some really interesting things with that. And so, by the way, Floodlight ships with a lot of modules already, so you may find a lot of things that maybe aren't enabled, but you could actually be really useful to you. So this is a very, very simplified view of the Floodlight architecture. So assuming you just start and run Floodlight, you have a list of modules in a config file. These are all the modules that Floodlight will recognize as valid modules when it first loads up. It'll try and load all those modules in the list. So it has two lists: one list of valid modules and another list of modules you want to actually load. So as long as your modules in both those lists will be loaded, assuming the code exists. And after your modules load, the REST service starts. And then what's called the Floodlight Provider Service starts. And the Floodlight Provider Service is essentially the core of the program. It manages the lists of modules, and it handles all the low-level packet and OpenFlow stuff that you really don't want to have to deal with. But you have to. So here is a very detailed view of the Floodlight architecture. And so everything over in this blue box, this is what the Floodlight Provider Service does. So for example, there's link discovery, for caching, topology management, device management, lots of things that have been done for you already that you don't want to have to do again. And that's covered for you in the Floodlight Provider Service. And then on the left here, you have all the modules that are higher level. There's a firewall, authority module that implements the learning switch functionality, which is also done a little bit. And you can also add your modules that list if you want to. And all of that, your module can take advantage of any features that another module provides, and also anything that's within the Floodlight Provider Service. And on top of that, you have your REST API and any other What's the what? The R. I cannot make this image come down in the R in these. Okay, so anything with R has a REST interface. Yeah, I saw your name on it. So anything with R has a REST interface. Okay, so if you want to customize Floodlight off the shelf, it basically will mimic a traditional network, assuming it connects to an OpenFlow switch. So if you don't do anything at all, your network should work just fine, as if you had plugged in the switch and had done nothing. Now, if you want to customize your controller, that will allow you to do examples like I showed you before, with the research that we've done, and also some of the things that might be of use that are difficult to do with a traditional network. So, I'm not sure, I'd like to get this PowerPoint to you somehow. I'm not sure how I do that, but on this slide here, there's some useful links. So there's some tutorials and how-tos about starting off running Floodlight modules. There's also a very useful one for the REST API. So assuming you don't want to change Floodlight at all, you just want to run it, you can have access to the REST API, and that link will take you to a very well documented page on how you can just you can use the curl utility on Linux if you use that to get information from Floodlight just using an HTTP request, or you can make changes to Floodlight without actually having to modify the source code yourselves. There's also a link to the developers group. And what I'd like to do now is walk you through how to create a module using Floodlight. And then after I walk through the basic steps there, I'll show you a couple of modules that I've written and kind of show you how they work. And there's a link at the very bottom there to the most recent version of my code, which is on my web at Clemson. I'm Git challenged, so I don't have anything in Git probably the last couple months. I keep overwriting stuff on my own machines. So for right now, I just have it on my web, so you can go to that link and you can find my code. And you can go up to the directory above that, find past versions if you want to play around with some other stuff. Okay, so can you guys all see the text? Okay. Can everyone see the text on that? Or read it? So this is a VNC connection into my desktop on campus, which is running the Floodlight code for the vertical handover and mobility software, SDN application that we've written. So it's running right now, and let me so what I wanted to do there is I restarted it. I'm going to show you just through the log, and then I'll show you the actual code that does it. Through the log file, you'll see how all the switches will connect initially. First, how all the modules will be loaded, then how all the switches will connect to the network, and then you'll see some of the code you've written actually come into play by using some of the existing modules that Floodlight already had. So, can everybody read this? Yeah.
Depending on what you want to see.
Yeah.
I'll probably just point out.
Okay, so that's worse. Okay. Does anyone know off the top of their heads how to increase the text size in Eclipse?
Eclipse is notorious. Well, you can
I've tried the resolution. It doesn't want to.
well, good of you. Turn scaling off. Oh, this is much better. The only thing is you're going to be when you move that stuff around.
Right. Okay, so what you can see right here, maybe, is Floodlight is going through its list of modules, and then it's trying to figure out, of the list of modules you gave it, which ones are there, and then it's going to try and load them. So this is what happens every time you first start Floodlight, whether or not you actually add any modules as you go.
So does every packet go through the switch go through the everything?
No, it doesn't. And I'll show you how. So what you'll do is when you create a module, you'll register for a specific type of event. So for example, if you want to listen for a packet in message, which is a really useful thing to do, then you'll register your module for a packet in message. And so your module will be added to the list of modules that will see that message every time a packet in occurs. So not every module will see that message, only ones that register.
Not
Right.
every packet in the network.
Right. So only
If you already set up, say, a static flow entry that matches certain flow criteria, target that will directly get ported on the switch without even coming back.
Is that what the FPGA for ASICs that it sends from the reconfigure the switch at that end?
Right, so whenever we say we write a new flow entry, we're writing one new rule to switch saying that for this type of packet forwarded based on what I tell you, and never come back to me again.
Okay.
So initially, Floodlight performs a lookup to see what modules it has, and then it will go and try and start all the modules. You can see right here that I'm setting the OpenFlow port number is being set, so that's the port that the Floodlight controller is going to listen on for any OpenFlow switches. You can change that to whatever you want, but the default is 6633. And so still, all these are module initializations. And so then here's where it gets a little more interesting. So right where the mouse is, you can see there's a new switch connection. So we've configured, so the switches that are connecting here, these are OpenV switches that are installed on some Linux devices, on APs and on the WiMAX gateway behind our WiMAX base stations. And these switches are configured to look for the controller at my IP address, which isn't shown here, of course, and at port 6633. So the switches are always probing for the controller, and then once I turn on the controller here, they, one after another, all got connected to the controller, and the controller added them to its database of switches. Each switch, and this number right here, that's called a DPID, is a data path identifier. And every switch should have a unique one for your network, and that's how the OpenFlow controller differentiates between one switch and another. Okay, so there's a few switches get added here, and then another thing that happens is, so notice here there's a static flow entry pusher. One of the modules I wrote, I use an existing module, a static flow entry pusher, and for a particular switch that connects, I want to insert certain persistent flows on it right when the switch connects. And I don't have a nice diagram to depict this, but for the vertical handoff to occur on the network side, only one flow is actually needed to reroute packets from one side of the network to the other. All the other flows can actually match, but can remain there for the lifetime that the controller is up. And so you only need to insert one flow when a client migrates. So we can insert the majority of the flows right when the controller connects. And that's what's happening here. That's where all the static flow entry pusher stuff is. And so notice I have my DHCP server module, and that's where I'm adding the flow. That's the DPID of the switch I'm adding the flow on, and each flow has a unique name. And so the way I made my flow's names unique is I just added a string that was descriptive of what the flow is doing right after the DPID of the switch. And so each flow, and so naturally you want your flow on your switch to do something, so you want to match certain packets, and then you want to do something based on what those any packets and matches. And so for a flow in Floodlight, it's called an output action, an OF action. And an OF action, an OpenFlow action, can be one of many different things. A common one is a simple one, which is output. So if you receive a packet matching these criteria on a certain port, output it on another port. That port can be a physical port on the switch, or it can be the local port, also known as 65534, some port number. And that port will go to the local interface of the switch, which if it's OpenV switch, will send it to the Linux operating system or whatever operating system the switch is residing on, which is actually useful for our cases many times. You can also send it to the controller port. So in the case of our flows that were inserted to intercept DHCP packets, these OF action outputs here, we're outputting to the controller port. So any DHCP packet we receive, we want to send it up to the controller because our controller is actually acting as a DHCP server. So this is how we're getting this to work with other DHCP servers actually existing on our network. So any questions so far? And so there's just a bunch of that happening at the beginning here because there's a lot of flows that we need to insert for the vertical handover. Okay, and so at the very bottom, right before I killed it, you can see from the DHCP server module, which is the module that I've written, I received a DHCP discover packet that was matched by one of the flows that was entering previously, and that flow directed the packet we received on the switch up to the controller, which has now received the discover. And DHCP packets have what's called a parameter request list, so a client can request many things in a DHCP request, like a gateway or router IP address. It can request a particular IP in case it comes back to a network that wants to have the same IP, and that's typically done. So I parse that list of DHCP request parameters, and I try and give everything I can. There's a lot of special Windows requests. I'm really not familiar with what those are, so I just didn't implement them since we're not using Windows. But so I try and honor as many requests as I can. And so here, you can see where I've mapped now an IP address to a particular MAC address. And then, so this is that you see it twice in there. This is a WiMAX adapter. This is coming to the WiMAX side of our vertical handoff network. We're trying to work on getting a particular WiMAX adapter to work. And so what it's doing is it's sending requests over and over and over again. And so that's why you see it duplicated here twice. Okay, so does anyone have any questions about just that overview? So what I'd like to do now is just walk through. So what I'm going to show you first is the main code. This is what's executed when flow bytes first run. So just verify that what I showed you before was accurate. So what happens is a file with a list of modules for flow bytes provided, and that file gets parsed, and all those modules that you're trying to load get attempted to be loaded through the floodlight module loader, which is right here. The REST API service will be started after that. And then here's that iFloodlight provider service. That's the core of the floodlight controller that gets started that gets instantiated last. And then here we're running the iFloodlight provider service, and that's what runs the entire program. Notice that's the end of main right there, nothing else really happens. So everything is entirely contained in iFloodlight provider. Okay, so typically what you want to do to create a module in Floodlight, it's actually really simple. So everything in this list to the, everything in this panel to the left here, these are all modules that are installed on Floodlight already, with the exception of this DHCP one that's expanded here. You have a lot of core processes. Here's the device manager that you saw in the graphic before. Here's the forwarding module that you also saw. There's link discovery, and the scroll bar is way up here, and so the list is really, really long. And so you can easily add your module to this list here. All you have to do is say new class, and then you can So after you create your module, most modules reside within the net.floodlight controller tab. And so you can add your module, just whatever you want to call it. So I call this one test module, because I'm not really going to do anything with it. But once you add your, so we've defined our module here. What you'd like to be able to do is add it, or make it implement certain things that are compatible with Floodlight's module loader. So basically you can for example, listen for packet-in messages or listen for new switch connections, and those are executed. So your module gets put in a chain of other modules that will see that event, and then there's a common methods within your module and other modules that will be executed when that event occurs. So you need to implement a particular interface depending on what type of event you want to do something for, like a packet-in. So you can add an interface to your module down here. And so a common one to add, of course, for a module is the floodlight module interface. These are all the methods. It'll go ahead and pre-fill all the methods that you need to have defined in your module in order for it to be a valid floodlight module. And another common one would be an OpenFlow message listener. And this will allow you to be inserted into this will give you the methods you need to implement in order to be added to the list of modules to process a packet-in message, for example. Notice here there's also a switch listener interface. This is what I use to listen for switch connections. So notice, remember when I started up Floodlight, you saw all those switches connect, and after those switches connect, I inserted particular flows based on what switch connect. So I implemented the switch listener interface, and then I registered my module to listen for new switch connections. So if a specific DPID of a switch connected, I would be notified because I'm a switch listener, and then I would insert flows on that switch depending on what its DPID was. Okay, so once you add any interfaces you want your module to work with, you just say OK. And so here's my new test module Java file that got created for me after I clicked finish. And all these methods are overridden methods that were inserted automatically depending on the type of interface we want to implement, or want our module to implement. So here, every module needs to have a name, so you can just specify. So when the module loader tries to load all the modules, it'll call your getName method, and you just specify whatever name you want the module to be referred to as within the Floodlight controller. These two here for is callback ordering prerequisite or postrequisite. Those are if you want your module to listen for a certain event. Say for example, you want your module to receive the message, like a packet-in message before another one. A good example of that is the DHCP module I have. So I want the forwarding module to run automatically because I don't want to disrupt any other network traffic that is going through these Open vSwitches I have. But what I would like to do is I'd like to have my DHCP server module always get the DHCP packets before the forwarding module gets them. Otherwise, the forwarding module will just take the DHCP packet and forward it, and I won't even have, so it'll go to whatever other DHCP server is on the network. And so the client might get 2 DHCP replies, and we don't want that, right? So using these two methods here, you can specify what modules you want to be loaded after yours, and what modules you would like to look at the message before yours, and what modules you would like to see the particular message after yours, like the packet. So you can also register your module, or you can also have your module implement services. I haven't actually done this myself, so I'm not an authority of speaking of what types of services your module can actually implement. Dr. Wong, do you know of any?
So if you want to leverage some of the existing services, for example, I wanted to know what are the list of devices that's currently connected, then you probably will declare that I want to get the service for, actually I was saying the dependency, so you can call on other modules that's currently existing and get information there. The get module dependencies is actually declaring whatever service you are implementing for others to deploy. Right? So you declare the name.
But the get module dependencies is for like if I wanted to depend on the if I wanted to use the forwarding module, right?
Right.
So I would insert that into my the get module dependencies.
Right, and
method
you can
here.
get dependencies with the device manager, you
Mhm.
can get the forwarding, all that. I think you were saying for get module services what it is about, right?
Yes.
And that is for others to retrieve your module service, whatever that you want. So you
Okay.
actually declare, if you look at some examples, you will declare your service, mapping to your module.
Okay, and so the next two here, these are initialization and startup methods. And so these are what are called when the module loading, or when the module loader tries to load your module. So you, things that you want to instantiate once, like if you want to get a reference to the floodlight provider service, you can do that in the init or startup function. And finally, this very last one here, this is where the bulk of your code will actually go, and this is what gets called. So in this test module, we decided to implement the IOF message listener, which is the interface for an OpenFlow message listener. So what it does is every time you receive an OpenFlow packet at the controller, which means a switch sent you something, you want to be able to receive that packet and do something based on it. And so this receive method here will get called within your module every time an OpenFlow packet is received. And so this is where the majority of your code will actually go down. And you'll see that in the DHCP code I'll show you in just a second.
Well, I'm not sure how much more time we have.
Okay.
But I think this gives a very good example on how a module is structured. And then a lot of the coding examples you can find on Floodlight web page, under the Floodlight project. So actually, I wrote several of the tutorials there. So then you can see a different granularity. You may want to implement something deep down in a module, or you want to deliver some other module to do some things, or you want to have this interface to connect to that service. Those can be, you can see it there, but I think it'll be interesting to see kind of the essence of how Ryan built a DHCP server using this module.
Okay, so what I've pulled up now is my DHCP server module, and it depends on, so I actually have, I told you before that I listen for OpenFlow messages, and I also listen for switch, new added switches, but actually I do that in two separate files. I'll show you that in a second. So I didn't come up with that idea until after I had made this one, so I just made a separate module, but eventually they will be incorporated together. But the DHCP server, what I'm showing you now, just listens for OpenFlow messages. And so at the very top here, I just have a bunch of DHCP stuff that I had to define ahead of time as members of the class, so that's not really important for the structure of a Floodlight module. But here, this is the first method that you saw previously, get module dependencies. And here, I want to say that I'm dependent on the Floodlight provider service, which is something that most any module would be. That allows you to access low-level networking features and OpenFlow features in Floodlight. So you'd almost always want to do that. So I say that I want to be dependent on that service. And then here's the init function. The init function is where I'm actually getting a reference to the instance of the Floodlight provider, the running instance of the Floodlight provider service. Another thing that I want to do in this DHCP server module is I want to have the ability to insert static flows. And what I mean by those is any flow that gets inserted statically is a flow that doesn't have any timeout. It's just something I want to insert. It's permanent unless I remove it, which is what we want to do in the case of a vertical handover. So I'm getting a reference to the static flow entry pusher service here. And this is actually the same thing that's used if you use the REST API and push flows that way. I'm just doing it within the Java code here. And another thing that's useful, and this allowed you to see some of the DHCP stuff before, is I want to be able to log stuff to the log file so I get a reference to the running logger. That's all within the init function. And then, let's see, after that, you see the startup function. The startup function, the very first thing I do is I tell the Floodlight provider service that I want to be added to the chain of modules that are going to be provided the OpenFlow message every time an OpenFlow message is received. And you can specify what type of OpenFlow message you'd like your module to see. So in this case, I don't care about, like, so some other OpenFlow messages are where Floodlight can learn about the features a certain switch has. I don't care about those. Those are a little too low level for the DHCP server module. All I care about is when the switch sends a packet to me. And so I'm registering only for packet in events. That packet in event is just whenever a switch receives a packet and it doesn't know what to do with it, so it sends it to the controller. So I'm listening for packet in events here. And that's again what allows my module to be added to the list that will be provided the packet in message. Next thing I do here is just a bunch of DHCP server stuff. And I'm getting a lot of options from a configuration file, which I have pulled up right here. So at the very top, you can see this floodlight.modules. This is a list of modules that Floodlight will read in every time it runs. And these are the modules that you want to be loaded. So notice here I have listed my DHCP server module. So when Floodlight first starts up, that's what tells Floodlight to actually load my module. So if I wanted to disable my service, all I would have to do is remove it from this config file, and I could restart Floodlight, but all my code would still be there. So just that one change would disable all the vertical handover functionality here. This other one here, this DHCP switch flow setter, that's the other module I briefly mentioned where I listen for switches. So that's before I have two separate modules. This one here listens for packet in messages and does all the DHCP work. And this one here, this one listens for new switches to connect and then inserts those flows to intercept all DHCP packets. I just have two separate modules to do it, but you can easily do it in one module. And you can also specify a bunch of configuration options in this same file here. So I just have a bunch of DHCP stuff here. The way you do that is, so remember the module we created for the test one at least was net.floodlightController. If I wanted to add a specific parameter for a config file for my test module, I would just say net.floodlightcontroller.testmodule with capital T and capital M. That was the name of the class. And then there you can specify whatever parameter you want. Right here is where I'm actually reading in those parameters. So let's see. So the actual reading of the config file is done at a lower level. In any module, you can just get a reference to the mapping of everything in your config file. So here I'm getting a reference to everything that started with DHCP server.DHCP server in this entire file here. And then based on that, I'm parsing all the information that I've provided in my config file. So like, for example, the size of the address pool, the range of the address pool. I've also got a spot where you can specify a list of MAC addresses for a static, for an IP that you'd like to be guaranteed for that list every time, things of that nature. And you can imagine you could add your own list of parameters depending on what type of module you want to write. You can just easily read them in this manner. And this is all doing the same thing. I'm just still parsing my config options. Okay, and that's it for the startup method there. Does anyone have any questions about initialization or startup? So it's basically just registering for the services you want to register for from existing modules, specifying what type of events you want to trigger the execution of your module, and also, or not the execution of your module, but any type of events that you want to pass to your module for handling, and just reading in config parameters and initializing things. That's all those two methods we're really doing. Okay, so again, like I mentioned before, I've never really done anything with module services, so this method I just left blank because I didn't need it. So anything you don't need that the interface completes for you, you can just leave it exactly how it is. You don't have to mess with it. It'll just be something that isn't included with your module. So in my getName method here, there's actually another one further down called getSimpleName. And I'm retrieving the name from that method. So I don't care about any, or I don't care about. So I guess you can think about this either way. So as far as telling what modules you want to load before and after, in this case I chose to use the post-rec method. So I said if a packet comes in and it's a packet in message, then, and I want to force the forwarding module to come after my module, to examine that packet after my module. And so that's what I'm doing in this is callback ordering and post-rec. I'm telling the forwarding module by specifying it here through its name. I'm telling that module to go to the to at least be ordered after mine. I can't specify exactly where, but I can say, I can ensure that I get a packet before the forwarding module does, and that avoids the problem of having two DHCP servers handle this DHCP request, for example. Let's see. This is just DHCP stuff. Okay, I'll come back to this here if I have time, but let me get down to the bulk of the code. So here at the very top of the screen there, you can see this is the start of my receive method. And like I said before, this is where the majority of your code's going to go. Whenever a packet in OpenFlow message that is of type packet in is received, this receive method will be called. And it'll be called before the forwarding module, because that's what was specified in our post-rec method. And so, the message that gets passed to me is an OpenFlow message, but I want to treat it as a packet in, and this is typically what you do in almost any case, so I cast it as that. And then from there, you can actually look at the packet itself. And so from here on down, I'm actually stripping the layers off the packet to determine what type of packet it is, because, let's see. So the very first thing I do is I get the payload of the OpenFlow message, and then I'm saving that as just a variable ETH. And if it's IPv4 packet, then I want to keep on checking because it might be a DHCP packet. This is actually kind of a little outdated because of what we're doing now is we're in the flows, we're ensuring that only packets on port 67 or 68 UDP are being sent to the controller. So the flows are actually doing this checking for us. So this logic could be removed. But before, what we actually did is so an OpenFlow switch will only forward a packet to the controller if it doesn't know what to do with it. So you could actually implement this one of two ways. So assuming that the network just starts up and your controller connects, the switch has no flows in it, right? So if it receives a DHCP packet, it won't match anything. It'll be guaranteed to get sent to the controller. And so that will guarantee that we receive it. If we prevent the forwarding module from ever receiving that packet, then that will also guarantee that flows never get inserted for DHCP packets. Does that make sense? So there's one of two ways that you can do that, and so that's why I'm actually checking the type of packet here. But this actually isn't necessary anymore with the flows that I'm inserting beforehand. And so after I check if it's an IP packet, I can check to see what type of IP packet it is. In this case, I'm just checking to see if it's UDP. And as you can see, most of this stuff is pretty high level. You don't see me working with any hex or binary type stuff here. All that's been done for you. And honestly, if I can point out one problem with Floodlight is that there's so much stuff that's done for you already that you'll probably end up writing something yourself, and you'll realize later that it's all been done, and you'll feel silly about it, which is what I've done many times before. So in Eclipse, you can do the thing here.
So I would point out that maybe the checklist to look at that real because what keeps me from sending some UDP packet on that port that's full of
Okay, that's a good point. Right. Okay.
So how much of the
Of the data in the I get the entire packet. Well, if you don't set the threshold,
By default, it's
you'll get the entire packet. So I haven't set any threshold, so I want the whole thing anyway. Yes, yes. Okay, and so after I check if it's DHCP packets, for those of you who don't know, are just UDP packets. So, and DHCP operates on UDP port 67 and 68. So I can just look at the next layer, or the next header in the packet and check the port number, and then from there I can determine for sure whether or not it's a DHCP packet. And let's see. I don't think I need to go into all these details here. It'd be kind of difficult to explain, but this is just a lot of DHCP logic, so I tried my best to implement as RFC compliant of a DHCP server as I could. So a lot of this I'm just trying to do that. So it's just a bunch of code doing DHCP stuff. This part here, starting with the synchronized, that's just ensuring that only one thing has access to the DHCP pool at once. So I don't want to have a race condition or something like that, where I try and issue the same IP to two different devices. So that's what this block is doing here. And down here I'm actually granting releases. Notice I have a function send DHCP offer there. So pretty much everything else is just high level, or it's just DHCP type stuff. You've seen pretty much everything that is related, that is generic to any floodlight module. I guess one thing I could point out at the very bottom here, well, oops. No, of action? Yes, that's what I was going to show you just right now before it cut off. Just my connection's flaky. It's this adapter here. I have to hold it down for some reason to get it to. Okay, so here, actually I'll go up to the first one so you can see the. So I have a method here called update client location, and that's what I use whenever I determine that a client has migrated and I want to update that the client has moved to a different spot in our network, so that we can insert flows along each hop in our network level of the vertical handover, so that all the packets will be routed to the client's new location. And so to do that, you have to insert an OpenFlow flow. And that's called an OF flow mod. And this is something that's very common, so I guess this could be, because it could be arguably general to any module, because it's common to want to insert flows. So you start off with your flow, and then something called an OF match, and that's the criteria that you want your flow, or that's the types, or the header attributes of the packet that you want to match this particular flow. So you should instantiate those, and then for each action, there's a very long name here, OF action data layer destination, and that says that I want to create an action for that OpenFlow packet that, or for any packet that matches this flow that modifies the destination MAC address of that packet. And so likewise, there's also objects like this for, of course, OF action data layer source, which could rewrite a source MAC address if you wanted to. Also, there's network level rewrites that you can do. You can also rewrite port numbers, VLAN IDs, anything like that is an object for you to add as an action to your flow. And right after that, I have a list of actions. So in this case, I only have one action. I want to rewrite the destination MAC address of any packet that matches this flow. But in a general case, you have to create a list of all the actions that you want. And you just simply append every action that you create to this list. And at the end, I'll show you give this list to the flow right before it's inserted. And so everything up here, this is just creating all these objects. And here I'm actually specifying what I want this flow to match. So I'm saying set the input port of the switch. Again, everything's pretty high level in Floodlight. So OFPP local is the local port of the switch, that 65534 port. So if you were running an OpenV switch, for example, that would correspond to, so say you want to write something in your operating system that, in the Linux operating system, that sends something into the network, you can listen on this port, and anything that comes from your OS will arrive at this port. This is what I have configured with C, for example, that port number. But it would be, of course, whatever name your interface actually is. And I'll say what we actually do here is our vertical handoff network is behind NAT. And so rather than trying to do all that within Floodlight, since that's implemented pretty well in pretty much any, for Linux at least, we actually send all of the packets that are outbound from our private network up to Linux, tell it to do NAT for us, and then have another flow that listens to the packets after NAT happens, and then we take it from there. So we just kind of offload that work. And that's why I'm actually using this local port number here. Okay, so I want to match anything coming in on this port that is an Ethernet IPv, or it's an IPv4 packet. Now I want to say anything that's destined for this particular IP address here. And so in this case, it's whatever client, anything that's destined for the client that we have migrating in the network, we want the flow to match that. And so again, I guess the big thing to take away from this is not specifically what I'm doing, but this is just typically how you would add something to a match on a flow. It's just as simple as that. Whatever your match is, set the input port. You want to match on the source destination MAC address, source destination IP address, port number, VLAN, anything like that. Yes, and so once this rule gets inserted, all subsequent packets will match this rule, and they will not be sent to the controller here. There is not. So it doesn't work. It doesn't work for a static flow pusher. There is the timeout.
Oh, yeah.
It's static.
You're using the static flow pusher, which is an existing module. By definition of that package, you see that as static. But based on OpenFlow, you could have a non-static flow pusher that duplicate the same thing, but allow the timeout to be
Right. So. So there's two different types of timeouts. You have an idle timeout and a hard timeout in general. So a hard timeout, no matter how many packets your flow is matching or has matched or is currently matching, it will just expire after a certain amount of time. And the more useful one, I guess, is the idle timeout, where if you don't see activity for a certain amount of time, then your flow will just disappear. And that's actually what happens with the forwarding module. So if anything gets, or if you want your switch to act just like a learning switch, those flows, you want them to expire after some time, otherwise your flow table could become very large. And so the idle timeouts get used in that case. Okay, so after I set what criteria I want this flow to match packets on, after that, remember the only action I wanted this flow to perform was just to rewrite the destination MAC address. And so for reasons unknown to me, you have to set even though this is declared, so DL dest action here, I'm declaring that it's an instance of an OF action data layer destination. I still have to tell it down here that it's a set data layer destination action. And then there you specify simply what MAC address you'd like this flow to rewrite packets to. So any packet that matches this flow, that matches any of these three criteria up here, the destination MAC address of that packet will be modified to whatever the current MAC address here. So remember, if you want to be able to use different interfaces on a client and have it be mobile, each one will most likely or should have a different MAC address. And so I say this is just a DHCP server method here, get current MAC address in bytes. That will retrieve for me the current MAC address my client has been detected to be using, and then I'll have the flow rewrite to that MAC address. And of course, another thing that you want your flow to do is you want it to output on some port. So this see, OF output action here. Of course, it's an output type. And then you can set the port that you want this particular flow to output anything on. And so I have something defined from a config file here, and that's just the port number I'm choosing. So after you specify all your actions, so for us we only have one, and we added it to the list right here. Let's say you have more than one thing, it's useful to have a list. So you take your, where is it? Stop here somewhere. Flow.set actions, and this is where all those actions I defined up above, I'm adding that list of actions to my flow. And also right here, all the match parameters I defined above, I'm adding that to my flow. And you can also give your flow a priority, which was briefly mentioned before. The higher the number, the higher the priority of your flow. And this is actually the highest it can get. So, and after that, you want to set the length of your flow. And this is the length in bytes that your flow actually is, that's used to transmit your flow to the switch. And for us, every flow has a minimum length that's just defined by what a flow for OpenFlow. And we decided to have an output action, so that has a length, but we also rewrote the destination MAC address, and that also has a length, because we're adding those two parameters to our flow, which don't necessarily have to be there, so we have to add those to our length. And here's where I give the unique names to my flow. And then, remember in the init function, I got a reference to the instance of the static flow pusher. And so I'm calling the static flow pusher's add flow method with the name I just set the flow here, the flow that I configured in all these lines right here. And then this is the switch that I want the flow to be inserted on. So the bulk of the work is just in defining what your flow actually is. Where you want to insert the flow, it's only one line of code. It's not hard at all. Like for you mentioned timeouts before. Like if you want.
Well, I guess you define the rule. The rule is this generic abstract. So I'm supposing the rule should be pushed to translating the OpenFlow protocol by the static flow.
Yes.
Or it could be translating the OpenFlow protocol and sent to the requesting switching pickup line. So is the static flow
It could be done in a different way, but the static flow pusher is done for you. That's the reason I've been using.
So you have to. There's only one way that you take the flow model, the rule, formulating the OpenFlow message, and static flow pusher already.
I had to define everything for the HTTP to do what you did. Static flow pusher defined everything you need to do static flow, so you don't have to do it. But you could.
And then you can actually dive into the static flow pusher and you see that it's just a bunch of sequence that you will package it into message and then
Does it the static flow pusher produce itself those two reactions from the rule?
it's only archiving service that will store that persistently in static flow as well.
Okay, so one of the last things I wanted to show you here with respect to flows is that just as easily as you can add a flow with static flow pusher, you can also delete a flow, which is what I'm doing right above the yellow box there. So it's my instance of static flow pusher dot delete flow, and then you just have to specify the name of the flow as you named it originally, and that flow will be removed from the switch. And so that's how I actually manage switching or sending the packets, routing the packets from one location to another on the network side of the handoff code.
Stay as long as keep going.
Yes, it would. It's pretty much.
I just pointed out properties for obvious. This is an example of the server. You can imagine anything you want. What if, for instance, purpose of a firewall, you have to funnel traffic in a particular device that does it. I think it would be also cool if the network is and this is implementing the DHCP server, which is also known as a standalone thing. You got a pretty good funnel traffic to DHCP server. Instead of these things being physical boxes or software modules.
And then there are these firewall manufacturer Apples or whatnot. So for anyone interested, you can just Google for Fortnite and then there's a simple instruction, just get the whole thing. You can read through that and just have a feeling of what are the kind of things that you know. But it's really meant for prototype tutorial for students. So as you look at it, if you see something that's particularly interesting, you can always think about how to make it more fully.
So,
Thanks for that. I'm sorry we have to run. Thanks for coming. Everybody coming out. Good to see your students, Ryan. And, hopefully we can make some progress on this. David, meet again maybe with some deep questions.
That's why we're going to do this.
Thanks.
there's a couple, unless anybody has to go right away, there's a couple more things I just wanted to mention. I'm almost done. But this here, this is, remember I said I separated the listening for switches and listening for OpenFlow messages into two different modules for this. It doesn't have to be that way, that's just the way I chose to do it at first. This is what it looks like if you want to listen for a switch. So there's this method that's going to be called automatically within your module called added switch. And there's also one, I'll show you at the bottom, for remove switch. And so in this case, I want to listen for all my switches that are going to participate in the mobility network to connect to the controller. When they do, depending on the particular switch ID, the DPID number, I want to insert certain static flows into those switches. So the way you do that is simply by, remember when we created our test module, we said that we wanted to implement the iFlow module interface, and we also wanted to implement the IOF message listener interface for switch, for OpenFlow packets. In this case, I simply implemented the IOF switch listener interface. And so it gave me all of these empty methods to fill in the blanks with whatever I wanted to. So in this case, depending on the switch that connects, I want to insert certain flows. So I just prepare those objects for the, so here's the flow object, there's the match ones, it should be similar to what we just saw before. And here's the list of actions, and there's the output action, which is the only action that I want these flows to have. So if you wanted to rewrite maybe if you wanted to rewrite an IP address or a port number, you'd have a different output action for every different thing you wanted to modify about the packet in the header. So basically what I do from here is I have every switch must, so because this is a test bed we've created, it's, we have a config, I just kind of have a config file with all the switches that I want to participate in this test bed. So there's relatively few of them, so I just have a bunch of if, else if statements to check to see what the DPID of the switch is here. And so you can actually see that in here. So here's the DHCP server parameters. So if you want to specify parameters for a different module like I did here, so it's, I'm still in the DHCP server package, but the name of my module here is DHCP switch flow center. So, and then this is the particular parameter, or the variable, and I'm defining this as the DPID of the switch. So I'm just reading those parameters in, that's what these variables are right here. So this is just a string DPID. And then from there, I'll set the flow parameters just like we did before. I add the flow, and then I clear the list. I'm just reusing all the declarations I did up top for all the flows that I insert, and that's for every DPID. So this is just an example of how you can, instead of listening for OpenFlow messages, you can listen for switch connections instead. So I add all the flows there, and so one thing I realized when I was running this is that when a switch disconnects, the flows get removed. So for static flows at least. So when the switch disconnects from the controller, all static flows will be removed when it loses connection. So there's really no need to remove all the flows that we inserted already. But if you wanted to perform some action based on a switch disconnect, you could put that logic in this method here, using something very similar to what we did above. So, any questions about this logic? So the last thing I wanted to show you was the REST API. So let's see. And so for that, I actually have a bunch of scripts, and I'll just show you this one here. So this is as simple as it gets for a command to full bytes, or a message to full bytes REST API server. So in this case, the controller is running on this machine, so I'm sending this. This is going to localhost. Port 8080 is the port the REST API server operates on at flow bytes. And this path after here, this is just whatever function you want to perform using the REST API server. So in this case, I want to look at all the, I want to, what is this? So yeah, in this case, I just want to get what does every switch look like from the controller's perspective. And I'm piping it to this mJSON, or this JSON tool in Python, and that will just take the string and pretty print it for me in the terminal. So right now the controller is not running because I stopped it earlier, so I'll just run it. And so all the switches are going to connect again. The modules will load before that, just like they did before. So I actually did it up there, but so there's the script that one-line script I had. I just pulled up in the window, so I'll run that. You don't. I don't know why I did that, but you don't. So here's the what the REST API command returned to me. So these are, so one of them is a Pika 8 switch lab. Yes.
Yeah, the D4, D9, D8.
Yes. That's the, so 38.2, that's on WiMAX gateway. So this is a switch on the WiMAX gateway. I tried to, so if you have for OpenVSwitch at least, if you add the OpenVSwitch to so the GPIG of the OpenVSwitch that we set, it's the format perspective, it becomes the hardware address of the local port switch. So that's what that's why that MAC address looks so simple. It's just taking that from GPID. So this is just one thing we can do. We use this because in OpenVSwitch, you're supposed to be able to, so like on a physical switch, you have like however many ports in the front, 48 ports, and they're all numbered for you. And when you plug something up, you know you're plugging in that port. But with OpenVSwitch, you don't know what port you're necessarily using because it's a virtual port. Now there are commands with OpenVSwitch to set a virtual port number, but they don't work. They're supported, but they just never actually do anything. And so if you want to be sure about your port number, you can actually use for like REST API. And for example, here, this is an OpenVSwitch bridge. It's called VR-Fake. This is some weird thing you have to do with VLANs with OpenVSwitch. Here's the port number, that's 65534 port. That's the local port of this OpenVSwitch bridge. So you can use this REST API command, for example, to get information such as port numbers from that perspective, without actually having to run a module to do it yourself. Here's another one up here. You can see that on the wall. That's port 15. That's just another port on the OpenVSwitch bridge. Does anyone have any questions? I think I've talked about everything I need to for the modules. Just one thing to note here is So all within this same Floodlight project, I also have all the steroid OpenFlow service code, and that's all within this module down here. Now notice that steroid OpenFlow service isn't running right now, and that's simply because in this Floodlight default.properties file, if I wanted to run it, I would just add a net dot. I would just add that, save it, stop the Floodlight, rerun it, and then the SOS module would then run. And so you can perform all the same types of functions that I did in the DHCP server module, like listening to OpenFlow packets, acting on them, listening to switches, and I actually do all that in the SOS module. I just did a demonstrate back to it. I don't know. I hope so. It's just there's lots of problems with that switch, and you're having trouble working around it. The PK, having lots of problems with this. It connects to the controller fine, but it just doesn't want to fully send stuff with ones that we need to. We don't know why. I'm still debugging it. I'll figure it out next year. Yeah, hopefully so.